So the first example, we're going to find the error bound for the fifth degree polynomial for the approximation of e. So we need a fifth degree polynomial for e to the x, which is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial plus x to the fifth over 5 factorial. So the remainder for the fifth degree is going to be less than or equal to the maximum of the absolute value of the sixth derivative of f at x over 6 factorial absolute value of x to the sixth. So we need the sixth derivative, f of x is equal to e to the x, and f of 1 is e. The first derivative is e to the x, f prime of 1 is e. That goes all the way to the sixth derivative, which is e to the x, and the sixth derivative of 1 is also e. So that's less than or equal to 6 over e over 6 factorial times 1 to the sixth. So the error bound is less than or equal to e over 6 factorial. Which calculates to 0.00377. So the error bound is 0.00377. To find the maximum error when the absolute value of x is less than or equal to 0.1, we need the remainder to be less than or equal to the absolute value of the third derivative of x over 3 factorial absolute value of x to the third. So the first derivative is 1 over 1 plus x. Derivative of that is negative x over 1 plus x quantity squared. And the derivative of that, the third derivative, is 2 over 1 plus x to the third. So I have less than or equal to the absolute value of 2 over 1 plus x to the third over 3 factorial, absolute value of x to the third. To find the maximum of that, we're looking at, to simplify, which is 2 over the absolute value of 1 plus x to the third times absolute value of x to the third over 3 factorial, which is 6. And since the absolute value of x is less than or equal to 0.1, that means that x can be between 0.1 and negative 0.1. So to find the maximum, we're looking at x is equal to 0.1, substituting in that value. 2 over 1 plus 0.1 to the third, and then 0.1 to the third over 6, which becomes 0.0002504. And then looking at the value of x is equal to negative 0.1, which is 2 over 1 minus 0.1 to the third, negative 0.1 in absolute value to the third over 6, and that calculates to 0.00457. Since 0.00457 is greater than 0.0002504, the maximum error then is 0.00457. We want to find the smallest Taylor polynomial that is going to be centered using the e to the x Taylor series, substituting in x minus 1. So we need to look at the nth remainder. So we'll need the maximum of the n plus 1 derivative at x over n plus 1 factorial. Absolute value of x minus 1 to the n plus 1. To get all the derivatives, they're just e to the x minus 1. So the nth plus 1 derivative of x is e to the x minus 1. And since x needs to be between negative 1 and 3, we're going to use x is equal to 3 because e to the 3 minus 1 is going to be bigger than any other e to the a minus 1 if a is between negative 1 and 3. Derivative n plus 1 of the function of 3 is equal to e to the second. For the replacing e to the second for the max, e to the 2 over n plus 1 factorial, absolute value of 3 minus 1 to the n plus 1, which simplifies to e to the second over an x plus 1 factorial times 2 to the n plus 1. The Lagrange error bound needs to be less than 1, so we're going to make that less than 1. And then just continue to test numbers in your calculator until you can get that error to be less than 1 by substituting in the value of n is equal to 5. We get 0.6568, which is less than 1, so then n is equal to 5.